5.7 Lesson 1, Properties of Definite Integrals. Our objectives are 1, you will learn the properties of definite integrals, and 2, you will use the properties of definite integrals to help you evaluate definite integrals. These are the 6 properties of definite integrals that we'd like to go over in our lesson for today. And we'd like to begin with the first one, positive and negative integrands. Here's what you need to understand. Let's take a look at A in the upper right corner and B in the lower left corner. So for A, the function is f of x is equal to x squared, and we may consider, for example, the definite integral of x squared with respect to x from 0 to 2. And this definite integral will be positive because the function x squared is positive on the interval from 0 to 2. The graph of the function is above the x-axis, so we have what we call positive area. On the other hand, when you look at part B here, the function that we have is negative x squared, and if we integrate on the interval from 0 to 2 with respect to x, we have negative area because the graph of the function is below the x-axis on the interval from 0 to 2. So the value of this definite integral will be negative. And the reason why is because remember that we define a definite integral as the limit of a Riemann sum as the norm of the partition approaches 0. So when you're forming the Riemann sum, each term will be a product, and because the integrand is negative for all values of x between 0 and 2, each term from the Riemann sum will be negative, and when you multiply and when you add the negative terms, you get a negative sum. So we just looked at the first property, positive and negative integrands. The integral, the definite integral of f of x dx from a to b is positive if f of x, the integrand, is positive for all values of x in the interval from a to b, as we saw here, and negative if f of x is negative for all values of x in the interval from a to b, as we saw here, provided that a is less than b, and of course in our examples 0 was less than 2. Now we take a look at property number 2, reversal of the limits of integration. So consider the same problem that we looked at earlier, where we had f of x is equal to x squared, and we had the definite integral of x squared with respect to x from 0 to 2. Now, what if you had the definite integral of x squared with respect to x from 2 to 0? We can actually find what the value of each definite integral is by using the fundamental theorem of calculus. So you find an antiderivative of the integrand and evaluate at the upper and lower limits of integration, and that will give you 8 over 3 minus 0, or 8 over 3. And for the second problem, where the limits of integration are reversed, what will you have? Well, you have the same antiderivative because you have the same integrand. You will evaluate the antiderivative at the upper and lower limits of integration, and you will have 0 minus 8 over 3, which is, of course, negative 8 over 3. So what you notice is that when the integrand is the same and the limits of integration are reversed, the definite integral has a value that is the opposite of the original definite integral's value. So that's what this particular property states. Reversal of limits of integration. When you have the definite integral of f of x with respect to x from b to a, and if you reverse the limits of integration, the new definite integral will have the opposite value of the original definite integral. Property number 3 is sum of integrals with the same integrand. And let's take a look at what we have for the parabola. If I write the definite integral of x squared with respect to x from x is equal to 0 to 2, then we know that this is the graph of f of x is equal to x squared, and this definite integral would represent the area under the graph and above the x-axis between x is equal to 0 and x is equal to 2. It makes sense to think of it intuitively that if you divide that region into two subregions, from x is equal to 0 to x is equal to 1, which would be the blue subregion, and you divide it into another, well, the other subregion in our division would be represented by the area of the second subregion would be represented by this definite integral, and graphically it would be the area under the graph of f above the x-axis between x is equal to 1 and x is equal to 2. It would be this area. And and you can see visually that it makes sense that if you add these two areas, that would be equal to the original area that we had to begin with. And that's what the third property is stating. Sum of integrals with the same integrand. So if the integrand is the same, and you have limits of integration for the first one, 0 to 2, and then you divide the interval from 0 to 2 into two sub-intervals. I divide at x is equal to 1, and I go from 0 to 1, and then from 1 to 2, and I add the 2 here. It should give me the same value, because I would have the same area. And in the general statement, the limits of integration for the larger interval is from a to b. And then we have a value c that is between a and b, like what we had with our example. The value 1 was between 0 and 2. So we're now looking at property number 4. If you have an odd function, such as f of x is equal to x cubed, and the graph of an odd function has symmetry with respect to the origin. And algebraically, you have an odd function if f of negative x is equal to negative 1 times f of x. So for our particular function, we have f of negative x would be equal to negative x cubed, which is, of course, negative 1 times x cubed, which is negative 1 times f of x. So f of x is equal to x cubed is an odd function. The graph has symmetry with respect to the origin. And if you look at our definite integration property, it states that if you have, for example, the definite integral of x cubed with respect to x from maybe negative 1.5 to positive 1.5, that is equal to 0. And this will be true as long as the integrand is an odd function and the limits of integration are opposites of each other. And the reason for that is, if I were to represent this graphically, here is negative 1.5 for x, and here is positive 1.5 for x. And you can divide this into two subintervals, as we saw with our previous property, number 3. So negative 1.5 to 0 of x cubed dx plus 0 to 1.5 of x cubed dx. And when you do that, the first definite integral from negative 1.5 to 0 will represent this area, and it will be negative because the graph is below the x-axis. Whereas the second definite integral will represent this area, and it will be positive because the graph is above the x-axis. But you will notice that those two regions have the same area. It's just that one is positive and the other is negative. So when you add them, you get 0. So if f is an odd function, then the definite integral of f of x with respect to x from negative a to positive a is equal to 0. What about if you have an even function? The graph of an even function has symmetry with respect to the y-axis. So here we have f of x is equal to x squared. Algebraically, an even function will have this characteristic. F of negative x will be equal to f of x. So for f of x is equal to x squared, we have f of negative x is equal to negative x squared, which is equal to x squared, which is equal to f of x. So this is an even function. So this property here states that if f is an even function, and you have the definite integral of f of x with respect to x from x is equal to negative a to positive a, then here's what we're saying with this particular property. Consider this example. Let's say we have the definite integral of x squared with respect to x from negative 2 to positive 2. That would represent the area that is under the graph of f of x is equal to x squared above the x-axis from x is equal to negative 2 to x is equal to positive 2. So it would be the area of this first subregion plus the area of this second subregion. But the two subregions have equal areas. So you can actually simplify your work if you're using the fundamental theorem of calculus by saying, okay, let me just find half the area and multiply by 2. And that's what this property is saying. So you can start at 0 and go to a, in our case 2, of x squared with respect to x. That would give you half of the area. And then you can just multiply that by 2 to get the full area. And that's property number 4 for even functions. We now take a look at property number 5. We'll start with the second one. That simply says, if, for example, if you have the definite integral of x squared with respect to x from 0 to 2, let me change the integrand. So maybe you have 7 times x squared for the integrand, and you have the definite integral of 7x squared with respect to x from x is equal to 0 to x is equal to 2. You can see that the 7 is a constant, and what this property states is that you can factor out the constant from the definite integral and write this as 7 times the definite integral from 0 to 2 of x squared with respect to x. We will come back to the first property for number 5, but let's take a look at number 6 first. Upper bounds for integrals. So suppose you have two functions f and g, such that f of x is less than g of x for all x in a particular interval. So look at the two graphs that we have here. Here we have the function f, and here we have the function g. And on the interval from 0 to 4, we can see that f of x is less than g of x for all x in that interval because the graph of f is below the graph of g. And the function f, if you wanted to know what that is simply f of x is equal to x. And the function g, if you wanted to know what that is simply g of x is equal to x plus 3. So what is this particular property stating? If this is true, then the definite integral of f of x dx would, from, for example, 0 to 2 will be less than the definite integral of g of x with respect to x on the same interval. And that is intuitively obvious because we know this one represents the area under the graph of f and above the x-axis on the interval from 0 to 2. And because f of x is less than g of x, of course, this one will represent a greater area. It would represent the area that we see here all of that. So now we'll conclude by considering the first property from number 5, integral of a sum. So suppose we have this function here, f of x is equal to x, and suppose we have the constant function g of x is equal to 3. And suppose we have a third function that we will call h of x, and h of x will be the sum of the other two functions. It would be f of x plus g of x, x plus 3. This is also a very intuitive property. If you take a look at what we have here, we have the definite integral of the sum of the two functions f and g with respect to x on the interval from 0 to 2. And all this property states is you can write that as a sum of two definite integrals, where this would be our first function for the integrand, and this would be our second function for the integrand. And each of the two definite integrals on the right, you can easily see that the first one would represent the area under the graph of f of x is equal to x above the x-axis from x is equal to 0 to x is equal to 2. And the second one would represent the area under the graph of g above the x-axis from x is equal to 0 to x is equal to 2. So it would be all of this area. So the integrand on the left is the sum of these two areas, because it represents the area under the graph of h, which is the sum of f and g, above the x-axis between x is equal to 0 and x is equal to 2. It represents all of this area. And you can see that, of course, the green region that I just shaded includes all of this, plus the triangular region at the top, which has the same area as the blue triangular region from the bottom, which is, of course, right here. So that's all that is saying. Today we looked at some properties of definite integrals, and we demonstrated the properties of definite integrals by using examples and by using graphs.